we have our first invited talk by Sjoert van Velzen called Tidal Disruption Events in the Rubin Roman Era, a multi-messenger feast. Go ahead, Sjoert.
Yeah, thanks, Jesse. I'm really happy to be here. So can you see the title slide? Yeah, all right. So then let's go to the next slide. Can you see TDE? Yes, okay. Yes. All right, so before we get started after the break, let's just watch a little movie to get back into the groove. This one has some funky music. I hope that's coming through. You're looking at a black hole with some accretion disk. And then there's a star coming in the distance. Star is approaching. Getting stretched towards the black hole. Now it's disrupted. Immediately we get beautiful outflows. Some dust. And maybe some neutrinos flying away there. Okay, so I hope that was worth 2 minutes of my time, because you just witnessed a stellar tidal disruption event. So here is the official theoretical summary. You have a star passing within the Roche radius of a supermassive black hole. It's torn into streams, half remains bound, and then falls back on a timescale of months with a steep power law decay. And why are we after these things? These probe really accretion onto quiescent black holes that don't show any prior accretion. So you get a really clean look at what's going on, and can witness accretion on human timescales. But these things are rare. You have to look at tens of hundreds of thousands of galaxies to see one. So this talk is really about black holes. So I want to put some fundamental questions here. So are black holes described by the Kerr metric? And how did black holes form in the early universe? These are two really big questions. And how do we address this by studying tidal disruption events? We can address the first question by looking at tidal disruption events in high mass galaxies. This will become clear in this talk. And this question about the origin of black holes themselves can be answered by studying tidal disruption events in low mass galaxies, which still have some trace of how black holes formed in the early universe. So those are the kind of big questions that we're after, but we have an expert audience of transient astronomers here. So of course there are operational challenges that I also want to be honest about. What are TDE imposters? So how do we actually identify TDEs? This is important at this high mass end. And for the low mass end, there is another big question. Where is the optical emission from tidal disruption events coming from? So these are two big open questions that are also weaving through this review talk. So since this is a review, here is a spectral energy distribution, simply showing a galaxy. So we have radio, infrared, optical, soft X-ray, and this is a normal galaxy spectrum. Now a tidal disruption happens, we have transient emission in the soft X-ray. Here is a thermal spectrum in the optical UV, a different thermal spectrum well above this galaxy baseline. This is about 0.1 keV, and it's coming from the accretion disk X-ray, whereas the optical has a temperature of 10 to the 4 Kelvin. It's a few thousand gravitational radii, but the origin is debated. So these are the key observables summarized here. Here is a light curve. So this is the real data, and notice this is a log time versus log luminosity. So you have a rapid rise, a power law decay, and then there is a long phase up to thousands of years after the disruption where you can actually see emission from the accretion disk that forms later. So these are long-lived transients in the centers of galaxies. And with these various parts of the light curve, we can measure the black hole mass and the mass of the star that got disrupted if you have perfect observations and agreement among the theorists. So this is what we're after. Of course, we don't have such good data for every source. We do have a spectroscopic classification scheme, and I have to show this since there's so many supernova folks in the audience. And I think you will start taking this field serious when you have a spectroscopic classification scheme. We don't call them type 1 or type 2, but we have hydrogen dominated, hydrogen plus helium dominated, or helium only tidal disruption events. And these separate nicely into distinct photometric properties as well. And so this field is getting mature, and we can spectroscopically identify these sources. That's really the take-home message here. So what's the summary? It is still a young field. So what's the summary of the history? Right, the first optical discovery, perhaps most relevant for this talk here, was in 2011 with SDSS. And then if we fast forward to today, there are many optical transient surveys obviously going on, and we have about 50 tidal disruption events with sort of ZTF dominating the number counts now. So then if we go forward in time, of course, the Rubin Observatory is on the horizon. That should see hundreds of tidal disruption events per year, maybe more, depending on how well you can classify them. So that's of course, really the next big thing on the horizon. And then the question for this talk is, what will Roman give us, which will overlap partially with Rubin Observatory. So what is going to happen? So let me give you my order of magnitude estimate of the number of tidal disruption events that Roman can see. I read this beautiful reference survey paper by the Supernova 1A cosmology team, and they have a very accurate prediction of the number of supernova 1A that they will see. So, this is cosmology, so they must be right. And so if I take this number, and these are at redshift 1 to 2, signal to noise of 10 at peak, so keep that in mind. The supernova rate and the tidal disruption rate are both actually relatively well measured, and the supernova rate is 100 times higher. So there will be a few hundred TDEs in Roman data at this high redshift, which is tremendously exciting because these will be the highest redshift TDEs known. So what kind of science will you do with these big samples? I already mentioned black hole spin in my introduction. And this is what real data looks like with real model predictions. This is the rate as a function of black hole mass measured from the M sigma relation. So these are all real tidal disruptions identified up to now. Then there's this big jump here, and there's one data point here. And this jump is due to the black hole event horizon. And then the spin of the black hole actually determines how fast the rate peters out. So if you occupy this diagram with more data, you can measure the spin of quiescent black holes. That's one big topic that we have in mind with these large samples. If you can do this in 2 different redshift spins, it's even better. You can see how black hole spin is evolving with redshift, which tells us very directly how black holes are growing via what mode of accretion. And there is another reason to be excited to see tidal disruption events at high redshift, in particular with Roman. And that's because already at low redshift, we have this strange overrepresentation of tidal disruption events from which hosts they originate. So overrepresentation of Green Valley galaxies by a factor of 5, or spectroscopically identified post-starburst galaxy by a factor of 10. So you can just see that by eye here. This is a traditional color magnitude diagram for galaxies with the contours encompassing Sloan galaxies matched in redshift to all these tidal disruption event host galaxies, which are shown with the little colored symbols. And they all fall in the Green Valley, which is sparsely populated at low redshift. That's where galaxies are transitioning from star forming to passive. This is probably due to a higher concentration on average of galaxies in the Green Valley, which boosts the tidal disruption rate. So it's not a complete mystery why this is happening, and probably a recent minor merger boosts this central density. And that means that when we see tidal disruptions at redshift 2, we're really seeing this growth of an accretion of gas onto the central parts of the galaxy and how that's driving up the tidal disruption rate. So we should expect an enhanced rate, basically because at high redshift, almost all galaxies are in a green valley, right? Because they're all just forming their stars. So blue or green. Sorry. And there is good and bad news based on the temperature of tidal disruption events, because they're blue and they're persistently blue. So the fact that they're persistent is good because supernova cool. So you can use this to separate tidal disruption events from supernova. But because they're blue, there is a problem when you use Rubin data to identify them. And I'll show this in the next slide. So this is the temperature as a function of time. So you see these straight lines. So constant temperatures, pretty high temperatures. And here's a supernova spectrum from a real supernova 1A. Here's the near UV, G, R bands shown here at redshift 0. And you see different epochs versus relatively blue, and then quickly it cools, right? This is all familiar, but really well sampled here with the real UV observations. This is a spectrum of a typical tidal disruption event. So there is a lot of light here, much more light than in the UV compared to supernova. The peak is in the near UV. But now at redshift 2, this is the Y band, which is the bluest band of the deep survey of Rubin. So we're not really sampling the peak of the SED with these Rubin observations. So that is something to keep in mind when you do classification. Sorry. So now if we go to the extreme, can we get even to higher redshifts? So there are high luminosity tidal disruption events, and one really fun debated source is the session-15 LH, which is either the most luminous superluminous supernova or a really luminous disruption event. And about 1 in 10 of the TDEs are in this high luminosity class. There are more of these coming, so stay tuned for that. And then they reach a black body luminosity of 10 to the 45 ergs per second, so order of magnitude more than typical TDEs. So these you could see to redshift 4. And then the SED peaks nicely in the H band. So you have really, you start to resolve the full spectral energy distribution. And of course, there are also superluminous supernova at the epoch of reionization that people are after. So we've seen talks already about this, but keep in mind, there are also superluminous TDEs. So this is exciting. We can see this to really high redshifts. So here is the spectrum again that I already showed. So let's look at one other wavelength, namely the infrared. So here is another piece of emission that you can see, which is a much lower blackbody temperature, and it's due to dust reprocessing. So we see dust echoes from tidal disruption events. And let me explain how this works. 1 second, sorry. Okay, so we have a black hole, it disrupts the star, you get light, and we see the optical light first. This is a real light curve, an optical tidal disruption event. Now, all this UV emission from the TDE sublimates the dust. So you you reach a cavity at the sublimation radius of the dust that emits at the sublimation temperature. So you first see the near side of the cavity, simultaneous with the optical emission, then the edges. And then when the dust has fully traversed this cavity, the infrared light curve, due to this hot dust, starts to drop. And so you have very reasonably simple dust physics. You equate the observed UV flux to the emitted infrared flux. And then you can solve actually for the radius from the duration of the light curve. So you get a geometrical measurement of the radius and therefore the absolute luminosity of the flare. So this is really valuable information, and you also learn about the dust covering factor from the ratio of the TDE luminosity and the dust luminosity. And we find these to be typically 1%. So a little bit of dust gives you this beautiful infrared light curve. And this is the artist impression you should have in mind when you think of what happens. You have the hot emission, you sort of illuminate the inner part of a torus, or it can be a spherical distribution. And then you get these infrared echoes. And so, of course, this is exciting to try to find these with the Roman Space Telescope. But the dust SED peaks at about 2 micron due to its, it is a high temperature, but it cannot be even higher. So it's still near the K band. So if you go to too high redshift, you redshift this out of the Roman bands, except if we include this F250 filter. So in the shallow survey with about 20 square degrees, you still don't really expect to see too many of these dust echoes, unless the rate of TDEs is much higher than we think, because many of them are obscured by dust. So I think we'll hear more about that in the next talk. But there is a nice synergy possible, because there's also the weak lensing data, which is a much larger area. And so if you have an idea that there is a tidal disruption event already there from Rubin data, then even a single or 2 Roman data points can be really valuable to get a handle on this dust echo. So that's something to keep in mind also, maybe when thinking about cadences for the weak lensing survey. And now for the last part of this talk, I want to go to multi-messenger astronomy. And here's the same SED again, and let's see if we can learn something about EEV energies, or well, not EEV, PEV energies. So this is through follow-up of IceCube. So these are neutrino alerts issued, a few per year, and we follow them up with this wiki transient facility. And we had success there. There was one very high UV luminosity TDE that also happened to coincide with a neutrino. And this is the optical and UV light curve shown here at the top. You see the light curve from ZTF in the red and the green. It goes up, it goes down, and this is really a UV bright source. So there's much more energy coming out in the UV. It decays, there's maybe a plateau at late times, and the X-rays also decay really rapidly. So this is probably due to an accretion disk that forms, but then also quickly cools out of the band that you can observe in the X-rays. And then this dotted line shows the arrival of the neutrino. So that's a single neutrino, but since tidal disruption events are rare, even taking into account that it arrives late, which no one had expected, the probability to see this by chance is around 2.8 sigma. So that got us really excited. And then we started to gather more data for this source after that paper was published, because the NEO-EYES data of this transient was released. And we noticed that this has the most extreme dust echo in all of the ZTF nuclear transient survey. So this information was not used to establish this as a neutrino source, but it is part of its properties. So that motivated me to do a search of all dust echoes in NEO-EYES from nuclear transients from ZTF. So this is all public data. So that's just to show the power of these public archives. So you select infrared echoes in the infrared. You select dust echoes in the infrared, and then you can find you look for coincidence sources with neutrinos, and then we find 3 neutrino flare pairs. That's our main result. And because we study this in the infrared, we are kind of agnostic to what is powering this flare, which is important, I think, also in connection with the next talks. And the infrared is simply, this dust is simply just reprocessing whatever is happening at optical UV X-ray frequencies close to the black hole. The dust reprocesses this and makes the echoes. So if you use infrared properties to select the flare, you don't have to classify things as a tidal disruption event or a large AGN outburst, or that's not what we try to do in this search. We just look for extreme flares, and we find 3 of them coincident with a neutrino, and now the chance probability gets even lower. It's a 3.7 sigma result.
Short,
So
5 minutes remaining.
Yeah, thanks. So I think that's also brings me to the conclusions. So Roman will detect a few hundred high redshift TDEs, redshift 1 to 2, and then a handful of even higher redshift nuclear transients. Now, this is a photometric classification challenge, of course, because you're missing a little bit of the peak of the SED, but the fact that these sources show no cooling should be really useful to identify them against the background of lots of supernova. And of course, then we can think about targets for a spectroscopic follow-up as well. And then Roman is sensitive enough to detect these dust echoes from all nearby TDEs. So we just have to make sure that to find as many as possible. And then using these observations, we can start to disentangle this connection between seeing neutrinos from galaxies with these large dust echoes. So I'll stop there, and thanks for listening.
Great, thank you, Sjoert, for a great talk. Just a reminder, you can ask questions here in Zoom or in the Slack channel. And right now there's a comment in Slack, which I'll read. It's from Peter Brown. It says, the excess UV luminosity of TDEs compared to type 1a supernovae will help extend the redshift range at which TDEs can be detected. And we have also a question.
Yeah, although that's also what I thought when I prepared this talk. But you do need the coverage, because this is where the emission is coming from. But if you observe this at redshift 2, right, then there is no currently bluer band planned than Y band for Roman. So you have to. So I agree, of course, with that comment. There is this emission here at higher at higher frequencies, but you need the depth similar to the Y band data to get to it, right? So that's maybe this color is sort of not really good. I think it's not steep enough that you can get away with a sort of 1 magnitude more shallow. But maybe I'm not interpreting that comment correctly. But it's important to keep in mind that if you want to see that peak, you need to, at this high redshift, you need to have a Z band or something, which is not planned.
That one is in Slack. If you can talk more about it later.
Yeah, thanks.
Lots of questions coming.
Oh, sorry, keep going.
No, it's great. We have one from Kishle on Slack that says, hi. For the plot showing volumetric rate against black hole masses for different spins, does that assume all TDEs come from black holes with the same spin?
I think those predictions, are from monochromatic spin distributions in order to make that plot. Yes. So you can make these predictions also for a mixed spin, and then you get something different. You also have to, more importantly, you have to average over the IMF, because this maximum mass for visible disruption increases with stellar mass. So that is the biggest challenge. So you need to restrict probably to early type galaxies where the IMF is dominated by low mass stars, or though you don't have these 3 solar mass stars flying around.
Okay, another question from Seppo on Slack. Could you explain the physical connection between neutrinos and dust echoes in TDEs?
No, no, this is purely empirical. But I do think that the infrared itself is not producing the neutrinos, but it's a very efficient way to find these large outbursts. And then the neutrinos themselves, I think are created in the accretion disk. Other people argue that they are created in the outflows, which are created after you have this large accretion event. And maybe some people have said that they are created when the jet interacts with the torus. But the dust itself doesn't have any strong shock, so you need something else. So it's a tracer.
Okay, we have a comment from James in Zoom. It says that it may be interesting to combine Roman and Ultrasat data on TDEs as well as other time domain searches. The two missions should be flying simultaneously, and Ultrasat will cover 230 to 290 nanometers.
Yeah, of course. Yeah, Ultrasat is fantastic for finding TDEs. I think there could be a redshift mismatch to some extent, at least if you're thinking about redshift 2. But if you're thinking about lower redshifts, then absolutely, yeah.
All right, one more question on Zoom from Brad. Are the TDE rate estimates based on single epoch depth for the time domain survey? Would it be possible to see much more distant events with stacking given the longer time scale? And conversely, would the longer time scale make identification more challenging?
Yeah, good question. Yeah, so this is single epoch depth because because that's how these numbers are estimated for actually being able to do light curve classification. So then to answer that question, you have to figure out how easy can you still do photometric classification when you start stacking. I think I think you can go a little deeper if you're willing to make your life harder. Of course, the 2-year baseline then is almost not long enough. So that's important. These are long-lived transients. So it's better to have a 5-year baseline in the same part of the sky, especially given the time dilation. You want to be able to actually see these long-lived events to do the classification. So yeah, that's an excellent point.
All right, any last questions? All right, thank you again, Sjoert, for a wonderful talk.
Yeah, thanks.